In this episode, we turn to a question that becomes more important after deployment than it often seems during design. How does an organization prove that a live artificial intelligence, AI, system still deserves trust once it is already operating in the real world? A system can appear successful because it is fast, available, and widely used, yet still be drifting into weak, unsafe, or poorly governed behavior that nobody sees clearly enough to challenge. That is why mature organizations verify deployed AI through structured methods such as audits, red teaming, threat modeling, and security testing instead of assuming that early approval remains good forever. For a beginner, the most useful starting point is to understand that verification is different from simple optimism and different from casual observation. It is the disciplined practice of gathering evidence that the live system, the controls around it, and the people using it still match the level of safety, accountability, and reliability the organization is expected to maintain after deployment. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. A helpful way to understand verification is to compare it with routine monitoring. Monitoring is like keeping an eye on the dashboard while a vehicle is moving, because it helps the organization notice warning lights, changing conditions, and obvious signs that something may be going wrong. Verification is more like stopping the vehicle at intervals, opening the hood, checking the brakes, examining the tires, and asking whether the machine is still truly roadworthy under current conditions. Both are necessary, but they do not do the same job. A live AI deployment may show no obvious failure in everyday monitoring and still deserve deeper inspection through more deliberate methods. For a beginner, this difference matters because many organizations mistake absence of loud problems for proof of health. Verification exists to challenge that false comfort by testing whether the system still operates within approved boundaries, whether controls actually work in practice, and whether the deployment remains defensible now that it has been exposed to real data, real users, and real operational pressure. One of the most structured methods for verification is the audit. An audit is a disciplined review of whether the deployed system and the governance around it match what the organization said it would do, what policies required it to do, and what leaders approved before or during rollout. That review may look at documentation, approvals, change history, access controls, logs, model limitations, incident records, user guidance, and evidence of how the system is actually being used in practice. For a beginner, the point of an audit is not mainly to catch someone doing something wrong. The deeper purpose is to compare the real operating state of the deployment against the story the organization tells about how the system is governed. If the organization says the system has narrow scope, meaningful human review, strong documentation, and monitored performance, an audit asks whether those claims are still true now that the system is part of ordinary business activity rather than part of a carefully managed launch plan. Audits are especially valuable because deployed systems tend to drift not only in data and performance, but also in process discipline. A workflow that began with careful review may become faster and looser after users grow familiar with the system. A deployment approved for one specific purpose may gradually spread into neighboring tasks because employees find it useful and no one stops the expansion early. Documentation may become outdated. Change records may become thin. Access may broaden, and once clear oversight requirements may start fading into habit and assumption. An audit brings those realities back into view by asking practical questions. Is the live deployment still operating under the same assumptions that justified approval, or has real usage moved beyond what decision-makers originally examined and accepted? For a beginner, this is one of the clearest governance lessons in the topic. A system does not become well-governed simply because the original launch package looked good. It remains well-governed only if the live environment continues to match the conditions that once made the deployment acceptable. Red teaming provides a very different but equally important form of verification because it challenges the system under pressure rather than mainly comparing documents and controls. In red teaming, a group deliberately tries to make the deployed AI system fail, misbehave, reveal unsafe weaknesses, or act outside its intended boundaries. That does not mean random sabotage. It means structured adversarial testing designed to uncover weaknesses that ordinary polite use may not reveal. A red team may try unusual prompts, conflicting instructions, misleading inputs, abusive usage patterns, attempts to bypass safeguards, or situations designed to expose brittleness, overconfidence, and harmful output behavior. For a beginner, the easiest way to think about red teaming is that it forces the organization to stop assuming users will behave exactly as designers hoped they would. Once a system is live, it will eventually face confusion, pressure, curiosity, careless use, and sometimes outright manipulation. Red teaming helps the organization discover how the system behaves under those conditions before outsiders or routine operational pressure expose the same weaknesses in a more damaging way. Deployed AI needs red teaming in part because live conditions are far messier than development conditions. A system that performed well in evaluation may be easy to confuse once people begin combining tasks, improvising instructions, and using the tool in contexts that were technically possible but never central to the original review. If the deployment includes tool access, connected data, or action-taking capability, then red teaming becomes even more important because one weak response may not remain only a weak response. It may lead to bad routing, disclosure of sensitive information, unreliable guidance, or downstream action that users trust more than they should. For a beginner, this is why red teaming belongs in post-deployment verification rather than being treated as a dramatic extra activity reserved for only the most advanced systems. Many harmful behaviors are not discovered through routine use. They appear when someone pushes boundaries, exploits ambiguity, or combines conditions in ways that normal workflows do not surface clearly. Responsible organizations therefore treat adversarial challenge as part of proving readiness to stay deployed, not just part of preparing for launch. Threat modeling adds another layer because it helps the organization think systematically about what could go wrong, who or what could cause that problem, and how harm could travel through the deployed system. Threat modeling is often associated with cybersecurity, but in AI governance it reaches further than only external attack. A threat may come from a malicious outsider, a careless user, a rushed manager, a weak data source, a broken workflow, a compromised vendor dependency, or a harmful assumption built into the way the system interacts with people and processes. For a beginner, the strength of threat modeling is that it moves the organization from vague worry to structured reasoning. Instead of saying the deployment feels risky, teams ask where the exposure sits, what paths could lead to harm, what assets matter most, and what controls stand in the way of those unwanted outcomes. A live AI deployment is a connected environment, and threat modeling helps the organization see the full chain of exposure rather than focusing only on the model as though it exists by itself. Threat modeling becomes especially useful after deployment because integration creates new pathways that may not have been fully visible during development. Once the system is connected to knowledge bases, case management tools, identity systems, customer records, internal workflows, or approval processes, the number of ways something can go wrong usually increases. A weak answer may not simply be a bad answer. It may misroute a case, shape an employee judgment, cause a disclosure, trigger an inappropriate action, or quietly reinforce a pattern of unfair treatment that spreads through a busy workflow. For a beginner, this matters because post-deployment verification is not only about the quality of generated outputs. It is about the full operating chain. Threat modeling helps teams trace where the data comes from, where the output goes, what tools are connected, what permissions exist, and where a human is expected to intervene. That wider view often reveals that the most important risks do not sit inside the model alone. They sit at the boundaries where the model meets business process, data flow, user habit, and connected systems. Security testing is the fourth method in this group, and it focuses on whether the technical and operational protections around the deployed AI system actually hold up. This can include testing access controls, authentication paths, data protection mechanisms, integration points, logging quality, input validation, system hardening, permission boundaries, and resilience against misuse or compromise. A beginner should understand that security testing is not the same thing as red teaming, even though the two can overlap. Security testing often examines whether defined controls work as intended, while red teaming pushes harder on how the system behaves under adversarial pressure and unexpected tactics. Both matter because a deployed AI system may be weak in two very different ways. It may generate unsafe or misleading output, and it may also be surrounded by insecure infrastructure or poorly enforced permissions that create exposure regardless of model quality. Verifying the deployment therefore requires attention to both behavioral risk and technical protection, because a system can be impressive in one area and still dangerous in the other. Security testing also matters because many organizations still separate AI evaluation from ordinary technology security work as though they belong to different worlds. In reality, once AI is deployed, it becomes part of the organization's broader system landscape and inherits the same need for secure configuration, strong access management, monitored connections, and controlled data handling. If the deployment allows inputs from multiple sources, retrieves sensitive information, stores logs, or connects to operational tools, then weak security around those paths can create serious harm even if the model itself is fairly well behaved. For a beginner, this point helps bring the topic down to earth. AI governance is not only about abstract fairness and sophisticated model behavior. It is also about whether the live system is secured like any other important business system should be secured. A deployment that cannot protect its own environment, data paths, and permissions will struggle to remain defensible no matter how strong its original business case may have seemed. These four approaches are strongest when they work together instead of being treated as separate exercises. An audit may reveal that the approved use case has widened quietly over time, which then tells the red team which new conditions deserve challenge. Red teaming may uncover a harmful behavior that threat modeling can then trace through the wider environment to understand how it could create real damage. Threat modeling may point toward weak interfaces or permissions that security testing can examine directly. Security testing may confirm whether the technical controls that an audit assumed existed are really operating as expected in the live environment. For a beginner, this combined view is important because real verification is rarely accomplished by one method alone. Deployed AI is a socio-technical system, which means the live risk sits across technology, people, process, and context. The organization needs several ways of seeing the system if it wants to avoid blind spots, false reassurance, and the tendency to believe one clean review is enough to prove ongoing trustworthiness. Human oversight also belongs inside verification, because deployed AI is shaped heavily by how people use it, challenge it, and depend on it over time. An audit may show that review procedures exist on paper, but verification needs to ask whether those procedures are realistic under real workload. Red teaming may expose that users overtrust confident output and rarely question it under time pressure. Threat modeling may identify human shortcuts, unclear authority, or inconsistent escalation as important risk pathways. Security testing may reveal that privileges or approvals are broader than they should be because convenience slowly outran discipline. For a beginner, this is one of the most important points in the whole topic. Verification does not stop at the model or the infrastructure. It has to examine whether the humans around the system are trained, empowered, and operationally able to perform the role governance assigned to them. A claimed human safeguard that nobody can actually exercise in practice is not a strong control, and verification should be honest enough to reveal that. Good verification also depends on evidence and timing. Organizations should know when audits occur, when red teaming is triggered, how often threat models are refreshed, and when security testing needs to be repeated because the deployment has changed. A system may deserve deeper verification after a major update, after integration with a new tool, after a shift in user population, after a concerning issue pattern, or after the deployment expands into a more sensitive workflow than originally approved. Waiting for an annual review alone is often too slow if the environment around the system is changing quickly. For a beginner, the key lesson is that verification should be scheduled, but it should also be event-driven. The organization needs regular rhythm and reactive discipline at the same time. Just as important, the findings should be documented clearly so leaders can see not only that verification happened, but what was learned, what changed, what still worries the reviewers, and why the system remains active or was narrowed, corrected, or paused in response. Several misconceptions can weaken post-deployment verification if they are not challenged. One is the belief that because the system has been working for a while, it must already be proven. Another is the idea that monitoring dashboards make deeper verification unnecessary. A third is the assumption that audits are enough by themselves because they sound formal and authoritative. A fourth is the belief that only the most obviously dangerous AI systems need red teaming, threat modeling, and security testing after deployment. For a beginner, each of these assumptions is risky because they confuse familiarity with trustworthiness. A deployed system can look ordinary and still be accumulating weak practices, expanding beyond approved boundaries, or becoming more exposed as business reliance grows. Verification protects against that slow slide into overconfidence. It keeps the organization honest by forcing it to test, challenge, inspect, and reason about the live system instead of merely admiring the fact that it has not yet failed in a way large enough to attract public attention. A practical example can make the full picture easier to hold. Imagine an organization deploys an AI assistant that helps staff review incoming requests and suggest next steps. An audit might examine whether the assistant is still being used only for the approved classes of requests, whether review logs exist, whether change records are complete, and whether staff guidance has been kept current. A red team might try to manipulate the assistant into unsafe suggestions, sensitive disclosures, or confident errors under unusual inputs. A threat model might map how those suggestions move into downstream business actions and identify where over-reliance, poor escalation, or connected tools could turn a weak answer into real harm. Security testing might then verify whether access controls, logs, integrations, and stored records are protected well enough to support the deployment responsibly. For a beginner, the lesson is that each method sees something different, and together they provide a much stronger answer to the central question. Does this live deployment still deserve the authority and trust it is being given in everyday operations? As we close, the most important lesson is that verifying deployed AI is about proving continued trustworthiness with evidence rather than assuming early approval lasts forever. Audits compare the live deployment against the organization's promises, policies, approvals, and control expectations. Red teaming challenges the system under pressure and reveals how it behaves when real-world misuse, confusion, and manipulation enter the picture. Threat modeling maps how harm could occur across the full operating environment and helps the organization see exposure that is not obvious from the model alone. Security testing checks whether the technical and operational protections around the deployment actually hold in practice. For a new learner, these methods are best understood as complementary ways of answering one governance question. Should this system continue to operate in this environment, under these conditions, with this level of trust and authority? A mature organization keeps asking that question after deployment, because the world changes, the system changes, and responsible governance depends on proving that live trust is still deserved.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.